In this video we will go through an introduction to Chapter 1 and basically point out some important things to keep in mind in reading Chapter 1 of the Thermodynamics textbook. And of course the main thing that's going to keep showing up in other chapters is the first law, which is just saying we have so much energy and we can move it into different forms, but it doesn't disappear, we don't create it. So all we're doing with the first law is accounting. We're just adding up energy and it just happens to be in different forms. Now, what we're going to do is we're going to certainly make some simplifications as we apply this to various systems. And one is the ideal gas law, which most people will be familiar with. The notation we're going to use, this is the volume per mole. So it's an intensive property, and this is consistent throughout the book. The important thing about the ideal gas law is when we have an ideal gas, it means that the internal energy and the enthalpy only depend on temperature. That means if I want to calculate delta H for an ideal gas, it's the heat capacity times the temperature difference if the heat capacity is a constant, otherwise it's the integral. And likewise, if I want to calculate delta U, CV, and this is independent of whether it's a constant pressure or a constant temperature process. If it's an ideal gas, pressure doesn't affect internal energy or enthalpy, only temperature. So one of the important things to keep in mind when we're talking about thermodynamics is we're not going to talk about time. In other words, we can't predict rates from thermodynamics. What we can predict is equilibrium, meaning if I wait a long enough time, then this is where we'll end up in terms of phase equilibrium or chemical equilibrium. Another thing that shows up as we work with a single component system, and it follows from the phase rule. So the phase rule says the number of degrees of freedom we have for a system is the number of components minus the number of phases plus 2. So if I'm looking at a single component system, 1 minus number of phases plus 2 equals 3 minus the number of phases. So if we have one phase, we have to have at least one phase, then we have 2 degrees of freedom. And what that means, and we'll think about this in terms of the steam tables to make it easier to visualize. If we're looking in the steam tables, if we're given 2 variables, then this means everything else is determined. So if you know the pressure and the temperature, then everything else is fixed. The internal energy, the volume, the enthalpy, the Gibbs free energy, etc. But they can be any 2 variables. So if you know the pressure and the internal energy, or you know the enthalpy and the volume, or the temperature and the enthalpy. If you have 2 variables fixed, everything else is fixed, and it's a unique value in the steam tables. So one thing that you'll notice if you look at the steam tables and you look at liquids is that U, H, V, S, none of these change very much when we change the pressure. They're almost independent. You have to go to high pressure to see much of a change. And this is what then for liquid water we refer to as incompressible, because these are almost independent. So one of the things that this means is if I have a liquid and I know its temperature, then I can use the values for internal energy or enthalpy or entropy from the steam tables for saturated liquid. In other words, saturated liquid at the same temperature, not pressure. For example, if I have liquid water, 100 degrees C and 7 bar pressure, and I want to know, so it's liquid, I want to know its internal energy, what I'm going to do is go to steam tables, look at 100 degrees C and 1 bar, which is saturation, and use that, and I'm going to be very close to the value at 7 bar. So one of the terms that shows up doing the calculations in thermodynamics is steady state, and we want to distinguish this from equilibrium. Steady state means that at a given point, the properties don't change with time. But steady state is not equilibrium in general. Equilibrium means if we wait a long time, nothing changes, right? No change. We say a closed system, for example, has certain components. If we say it's at equilibrium, it means we come back next year, it's not changing. For a steady state, for example, flow system, I can have a chemical reaction occurring, and I can have something here is not at equilibrium. As I move down the reactor, I'm converting my reactant to product. I move further down, I convert it more. As I move further down, I'm getting closer to equilibrium, right? That's the way reactions always go. So it's closer to equilibrium, but it's not at equilibrium. But it can be at steady state. By that, it just means if I look at this location, the temperature, the pressure, the composition doesn't change. If I come back next year, it's the same values. Another important term that's introduced in this chapter that's going to be used throughout the book is this idea of vapor pressure or saturation pressure. These terms tend to be used interchangeably. Of course, this means if we have a system that has liquid and vapor, and it's equilibrium, and it's at constant temperature, T equals 27 degrees C for the whole system, both liquid and vapor coexist, then if I put a pressure gauge on here, the pressure I measure is the vapor pressure. It's a unique property of temperature for a single component system, right? So I'm just looking now at a single component system. If in this system I were to increase the temperature, so if I raise the temperature in this system, then I'm going to raise the vapor pressure. And the final aspect we'll look at this chapter is this idea of a simple potential energy diagram. Look at energy versus distance between molecules. And so if molecules get close enough together, then it's almost, in this case we're going to model it as just a hard sphere. In other words, as we try to push them closer, these repulsive energy increases dramatically. But there's some potential well, attraction, where they sit in potential well, they have attractive forces, you just can't get them too close together. And if they get further away, then they don't even know each other exists. There's no attraction far enough away. This, of course, is an approximation to what the actual diagram looks like, but it's one that helps us to visualize. So this relates to the distance between the molecules, the closest distance. And then the energy well relates to how attracted the molecules are to each other, how sticky they are. So if this energy well is deeper, then we expect the molecules have stronger attraction. For example, we expect they would have lower vapor pressure. And so that's just a quick review of some of the important aspects of this chapter. And keep in mind, when the steam table's here, this could have been also, I left out entropy. Temperature and entropy would be two variables that could specify, or enthalpy and entropy, or internal energy and entropy, and they completely specify the system.